everyone, in this lecture we're gonna have a look at some spatial patterns in very simple systems. So in particular we'll be looking at the article by John Pearson titled Complex Patterns in a Simple System, and this was published in 1993 in the journal Science. So he was working at the Center for Nonlinear Studies, and the question was whether complicated spatiotemporal behavior could be obtained through simple systems. And patterns such as this, stripes or islands, labyrinth patterns, cells, spots, even complicated labyrinths. So such kinds of patterns, they were shown by Pearson that such a system is able to give rise to these complicated patterns. And in this lecture, I'm gonna show an overview of the program, and the reason I say overview is because uh, this particular code would take a lot of time to write, much more than an hour if I explain it everything. So I've already written down the C code and we'll be going through how you go about this. Well, back in the day, there's a big difference on in how things were done back in the day versus how one would do it nowadays. So if you look at how he did it, so the simulations are forward Euler integrations of the finite difference equations resulting from the discretization of the diffusion operator. The spatial mesh is 256 by 256 and the time step is 1. And so they refined the mesh, they took a small time steps, and this led to no qualitative difference in the results, and the conclusion was whatever you see with this coarser, relatively coarser mesh is okay. And they had uh, near the origin they gave a perturbation to the system, okay, with a random noise to break symmetry, and once symmetry was broken after 200,000 time steps, they saw emergence of a pattern, and the pattern is actually classified depending on the parameters at play. So the parameters at play are f, du, dv, and k. So in our system we'll call this as phi and this as kappa. Okay, so depending on that particular parametric space of f and in our case phi and kappa, you will obtain one of these patterns. Okay, so B corresponds to uniform blue state where one product or one of the reactants dominates over the other. R corresponds to the red state where the other reactant dominates, while epsilon, eta, kappa, lambda, mu, they are all different patterns as seen in this figure. And you can see that the band in which those kinds of patterns occur is not very large. If you go to a zone over here, you will have completely blue. If you go to a zone over here, you would be completely red. So as such, you do not, I mean, you have a very small parameter space to play with. Okay, so you do get a host of interesting patterns, and so let's see how we can go about solving this particular equation. So the equation at hand is del u del t is equal to du Laplacian of u minus uv square plus phi 1 minus u, and del v del t is equal to dv Laplacian of v plus uv square minus phi plus k times v. So these are the two systems. So you can clearly see that these two terms are the reaction terms, and in this particular case u is being consumed due to the reaction, and V is being produced because of the reaction, and more V is produced per reaction because of the presence of V square. So what about these terms? So these are the sources. So because of the consumption in U, there is a source to make up for that consumed U, and it is this sort of balance between consumption and production that is sort of driving this particular nonlinear phenomenon. What about V? So there's a steady decay, a bulk decay, which is proportional to the local concentration, and this gives rise to an evolution of the equation V. So how can we solve such a system? Well, as has been told in the article itself, you can simply perform a discretization. So you have uij n plus 1 minus uij n minus 1 upon delta t is the diffusion operator on uij at time n minus 1. So this is an explicit method, but that is what exactly they did. They did the forward finite integration. So it's quite easy to do, and so I'll in fact let me write down the entire discretization, and you can take it as a challenge to program it using Python or Octave. So plus du uij minus 1 plus minus 2 uij plus minus 2 uijj. So these are all at n minus 1 time step plus uij minus 1 upon h square plus ui plus 1j n minus 1 minus 2 uij n minus 1 plus ui minus 1j at time n minus 1 upon h square. So you can see that this is the del 2 u del y2 term, while this is the del 2 u del x2 term. Well, now what about this? This is simply plus phi times 1 minus uij at n minus 1. Because of the sort of linearity in this particular term, you can actually take this to be at time n. And why is that? Because it does not break any explicitness of the problem. You can simply combine it with this particular term and obtain an expression for going from time n minus 1 to time n explicitly over each cell. Okay, so in similar fashion, we can write the governing equation for V as well. Everything's gonna look the same, and therefore you have what is called as the forward Euler integration FD scheme, as was done over here. And the delta t, you can choose it to be 1 when the diffusion coefficients are appropriately chosen, as mentioned in the paper over here. Okay, so that can act as a nice exercise for you to do. But given that you have extensive solvers available nowadays, what we do is club the linear terms or non-reaction and non-source terms to one side and have the other terms on the other side. So you can write, let's say that f of t u u prime, or if I write it down in terms of the y vector, so y vector is actually comprised of uv. This is what y vector is comprised of. So f, let this be equal to del u del t minus du Laplacian of u and dv dt minus dv Laplacian of v. So these are the two linear terms, whereas let me define g as the source and the nonlinear term. So t y, so it's not a function of t, so I can drop this particular t over here, and simply write it as y comma y. It's in fact not even function of y prime, so I can simply write it as g of y. So this would be equal to, so we want to cast it in the form f of whatever it is equal to g of whatever it is. So then these two terms have to go on the left hand side. So it will be u v square minus f of 1 minus u and minus uv square minus f plus k, or rather plus f plus k times v. So under these two, when we write it like this, we can write down the equation as f t y y prime is equal to g y. Okay, so now we have actually made a operator splitting into something which contains the time derivative and the spatial gradients, and the other operator which contains simply the reaction term and the source term. Well, in the above situation for the Euler method, I've written down the Laplacian in typical star format. So by star format, I mean if I'm writing the Laplacian at this point, I'm writing in terms of this, this, and that's it. So it's uij plus 1 minus 2 uij plus uij minus 1 by h square plus ui plus 1j plus rather minus 2 uij plus ui minus 1j upon h square. So when it's like this, you're writing it simply in terms of these terms while disregarding the contributions from this term. And usually it's fine, nothing fancy happens. But in such cases where there's diffusion and all that, you want to preserve the isotropy of the problem. There is another stencil which is appropriate, and that is based on the box stencil. So if you recall that when we declared our DMDA, there were two options. One was to declare it as a star. So DMDA for structured meshes, there are two options. One is to declare it as a star, which is this case, and one is to declare it as a box, where you have access to these elements as well. So when you account for this, you essentially have 8 neighbors to a given point, and you can write down the derivative in terms of them. In matrix form, I can write down this as something like this. So it's 1 upon h square, 1, 1, 1, 1, minus 4. Okay, because these two terms, they combine to minus 4, so you're writing it at I comma j. So there's one contribution from this, one contribution from this, one from this, one from this, and minus 4 from the center point. What about the box? So the discretization that many people have used in order to simulate what they call as the Gray-Scott systems, and actually this kind of things were analyzed in quite details by Alan Turing. So Alan Turing, if you know, he was the hero who was responsible for breaking of the Enigma cipher during the Second World War. Okay, so the Enigma cipher was a German encryption system with which they would send messages unimpeded across as radio waves, and no one could even understand what their plans were, but Alan Turing was able to solve this. It's just a little bit of history just to break the monotonous routine. So Alan Turing also studied such kinds of systems, and the general submatrix. So this is the differentiation submatrix. And the differentiation submatrix for a better discretization would be this. Oops. So this particular matrix gives us a better isotropic diffusion and helps us in removing some of the artifacts. But well, you can try your hand at the previous discussion, and it doesn't make a difference. It's order h square anyway. It's just accounting for more diagonal points, which is always a good thing. The larger your basis set, or rather the larger your submatrix becomes, the better you are at representing gradients. Okay, so what we have done is split the problem into two parts, which is an explicit part and an implicit part. So for the explicit part, we must construct the RHS. For the implicit part, we must construct both the implicit RHS and the submatrix, or rather the Jacobian, in order to solve it using the SNES. And in this case, the Jacobian will actually be a shifted Jacobian, where it's not just del G del U, in this case Y, plus it's del G del Y prime. Oh, sorry, we're gonna create the Jacobian not for the nonlinear part but for the linear part. So in this case, it will be del F del Y plus del F del Y prime. So you're gonna construct this Jacobian. It's called as a shifted Jacobian. And once you start learning the theories of all this, you will be more aware of what all these things are. But my hope is, once you do learn these things, or if you have ever learned these things, PETSc will enable you to implement them quite scalably on your home computer even. Okay, so that's pretty much it. And okay, so the domain in this particular case is going to be periodic. I have not drawn the domain. The domain over which we're going to solve the problem spans from minus 2.5 to 2.5, if I'm not mistaken, in both sides, and the origin is at the center, and all the boundaries are periodic. So it's periodic in both x and y. So with this background, let us go to the program. I've written down the program already. So okay, so we'll do two things. We'll first create the field structure, which contains simply the u and v. We'll create a structure which contains the parameters of the problem, which are going to be the length of the domain, the u diffusivity, the v diffusivity, the phi, and the kappa. So these are the parameters of the problem. And you will see the app ctx, that is the app context. It is being passed around to the functions so that you can construct everything in terms of the parameters that are being packaged under appctx. And the field is required to declare the 2 degrees of freedom per node that we have. Okay, so recall that we have declared everything as 1 degree of freedom so far, because we did not have a system of equations. But now we have at single node both values of u and values of v, so we declare it as a struct, and that struct is simply declared over here, and it's star star. Why? Because it's a 2D matrix. I mean, it's a 2D array. Okay, so it helps in definition of the not the definition, but it helps to sort of reference to the data. Okay, so let's see what the main looks like before going into the functions. So we have the declaration of the PETSc error code, IERR. I mean, you can make do without this as well. We've done a bunch of examples where we have not taken IERR as the output. But usually what you do is, whenever you call a PETSc function, the return value is going to be an IERR, that is a PETSc error code. And then you check the error code with this function chkerrq. But you don't need to do that, as you have seen in previous examples as well. Then you declare the appctx and assign it to a variable called as user. Then you declare the time stepping object, you declare the vector x, you declare the DMDA, you declare the DMDA local info, and you declare a noise level. So this noise level you can change and recompile and run the program. Alternately, you can fetch the noise level from the command line arguments, but here we'll do it through main as itself. Then you have PETSc initialize, which you must have always. Then you declare the L, du, dv, phi, and kappa. So let us look into the paper. So du was 2 10 to the power minus 5, dv is 10 to the power minus 5. what I have chosen is 8 10 to the power minus 5, 4 10 to the power minus 5. And phi and kappa are kept to be 0.024 and 0.06. So over here, various simulations are done, but where do we lie? 0.024, 0.6, 0.024, 0.6, somewhere over here. Okay. Alright, so phi, kappa, everything is defined. Then we create a DMDA, and this is the entire creation of the DMDA. So it contains a create 2D function, and here the stencil box will be the stencil will be of the kind box. It's not gonna be a star anymore. Okay, so here the number of degrees of freedom is gonna be 2, and that's it. And here the boundaries are declared to be periodic. So just for a reference, just for a reference, so we have bx by. Okay, let's zoom this out a bit. So a stencil type, which is stencil box. Then you have m comma n. So in this case, the default grid is 3 comma 3, and you have to decide. Let PETSc decide the number of the load balancing between the processes. You have 2 degrees of freedom. Stencil width is 1. Everything else is null, and you have to pass the address of the DMDA. This we have done this plenty of times, and there should be no doubt in this. Then you set from options in case you are passing command or arguments. You need to allow this. You set up the DA. Now you have to do DMDA set field name. So because there's 2 degrees of freedom, you're gonna call the 0 field as U, and you're gonna call the V field, the second field as V. So these two lines are used to define the alias for the 2 degrees of freedom over the entire grid. So the grid has 2 degrees of freedom. So the index of the first degree of freedom is 0, and it has an alias U. The index 1 has an alias equal to V, and then you fetch the information about the grid, because when you define the local functions for forming the RHS function or the Jacobian, you need to pass around the info object for the DMDA, so that you can perform the loops and all that thing. You can find out what H is going to be. Now here is something which we haven't used so far, which is DMDA set uniform coordinates. It's a very simple function which you can imagine what it means. It takes the default domain and it scales it between 0 and L. In this case, L is 2.5, so it's gonna scale it from 0 to L. So you have to pass the DA, you have to pass the X min, you have to pass the length, you have to pass the Y min, you have to pass this, and it doesn't matter what these two values are, because it's a two-dimensional problem, because you're creating a DMDA 2D. It doesn't matter what these values are, it's going to be ignored in the case of two-dimensional problems. Then we are creating the time stepper. So ts create PETScom world set dm. So this particular line is used to link the time stepper with the DMDA. Okay, so application context, so you have to tell the time stepper that okay, whatever parameters you're gonna have, they are stored under the variable called as user, so you have to pass the address of user. Then you have DMDA time stepping set function. Okay, so here you are setting the RHS functions and the Jacobians. Okay, so here you're doing the setting of the RHS function and the Jacobians. Okay, and uh, the time stepper type is TS Archimex, which stands for adaptive Ranjkutta Rungakutta implicit explicit. So it's a advanced time stepping routine, but we can use a crank Nicholson on anything. But in this case, this gives us the best performance, so I've written it like this. So you set the time parameters, that is the initial time, the max time, the time step, and so on. You can make this lower if you want, and you have to match the final point with the time step. TS set from options in case you are passing command line arguments. After this, you have DM create vector global vector DA. So this is fine. So you are creating a vector X based on the DMDA grid. Then you create an initial state. This is quite important because obviously 1 comma 0 is going to be a solution. So if you said u equal to 1 and v equal to 0, both these equations, the LHS and RHS, they match. It means that the system is having a trivial solution of u equal to 1 and v equal to 0. No, or is it u equal to 1? Yeah, u equal to 1 and v equal to 0 is a trivial solution. So in that case, that is not of much interest to us, and that is why we have to give a perturbation to the initial condition, and that is what will be done through the function initial state. So in order to find the initial state, we are going to pass. So these are all functions which we have to create. Okay, we will pass the DMDA, we will pass the vector X which will be iterated in time, and we'll pass the noise level, and we'll pass also the set of parameters that we have stored in the structure appctx called user. Then you solve it, then you destroy the variables, then you finalize. That's it. It doesn't appear to be much more complicated than what we have done so far. But now let us look at the functions. So first things first, let us create the initial state. So we have as an input to the function dA, the vector y, the noise level, and the appctx, which contains all the different parameters of the problem. So I'm gonna just tell you the logic what is going on. You set the vector to 0, both the u and v are their initialized to 0 through this point. After that, you set a random value of y, or you sort of set it to y, but then you scale that to the appropriate noise level. That is, you first set the random value. So let me show that function reference. Set all the components of a vector to random values. Okay, after that you scale them to the appropriate noise level. So vex scale will scale it to the whatever the random values are. It will try to linearly scale it between 0 to the scaled vector. So in this case, we can make it 1, or you can make it even smaller. Okay, so that is governed by the scalar noise level. And in the main, I've defined noise level to be 1, but you can keep changing it and recompiling it. You will get new solutions. Well, not really new solutions, but a difference in the time taken to evolve to the solution. Okay, that's all going to change. So then you get the local info, get the coordinate array. So you save the coordinate array in the from the DMDA into a variable called AC, which is a second 2D array. So that will contain all the x's and y's. And how do you call the x's and y's? So inside this AC j comma I dot x. So the calling sequence for the coordinates is going to be AC j I dot x or AC j I dot y. So this is going to give you the local x and y coordinate, something which can imagine to be of the kind mesh grid in Python. Okay, then you get the array, then you assign it with a random number, not a random number, you have already assigned everything to a random number, but in between L edge and R edge. So L edge and R edge are at the left edge and the right edge in the problem. Okay, so it's gonna be between 1 and 1.5 because user.l is gonna be 2.5. So 2.5, yeah. So here what we have is declare some analytical function on top of the random variables between x equal to 1 point, rather x equal to 1.0 to x equal to 1.5. So you're gonna set that to a random number. You're gonna set that zone, that strip, with a defined function. In this case, it is gonna be sine 4 pi x square times sine 4 pi y squared times half, and you're gonna sum it over all the domains. That's like the not the domain but the strip. While for u, you're gonna simply do 1 minus 2 v. So that is the initial condition for u. So with the help of this, you can create some perturbations in the initial condition. Lastly, you must restore both the coordinate array and the unknown array, that is u and v. Okay, so what about form RHS function local? Because it's being done on the function g, it's going to be done on the function g. So what is the function g? Okay, so it's going to be uv square minus f times 1 minus u. Well, over here I think I have taken the negative sign, meaning I have made this and this. So I've just, it doesn't make any difference. It's nothing is going to change. So it's minus uv square plus 5 times 1 minus u, and uv square times uv square minus 5 times 5 plus kappa times v. So this is obviously going to be av times av ay j comma I comma v. This is how you form the RHS function. How do you find the Jacobian? It's quite simple again. It's going to simply be Jacobian of so it's going to be the Jacobian of this guy, which is going to be, so dilute, this is going to be what, minus v square comma 0. So let's see where I have written it. So you're looping over the entire grid. So uv v2, so they're defined as u times v and v square. So this is going to be minus v2 minus f minus 5 times u. So when you take a derivative of this function with respect to u, you get minus v square minus 5, which appears over here. Then this is minus 2 uv. So when you take a derivative of this with respect to v, you have minus 2 uv, which is appearing over here. So uv is already declared as this double. It's a local variable inside a function, so it doesn't matter. Then mat set value stencil p comma 1 comma row comma 2 comma call. So this is just to set the preconditioner. Similarly, you have this, and you can easily verify it from the derivatives of that function, this particular function, and you set it. And like always, when you declare a Jacobian, you're going to fill in the preconditioner. Once you filled in the preconditioner, if j is not equal to p, you assemble the Jacobian anyway. If they are equal, you essentially are assembling the preconditioner, which is also equal to the Jacobian, and we have discussed this in the previous lectures. Now we come to the implicit part, that is, we have to form the functional, not the functional but the local function. So let's see what we get. Okay, so the derivative, so let's see. So you have this stencil. Look at this stencil. This is exactly this particular stencil that I showed over here. Okay, so it's Laplacian of u, Laplacian of v, but finally AFU will be a dot u minus the diffusion coefficient times Laplacian of u. Essentially, it's this term Okay, and the other function is going to be v dot minus Laplacian of v. Actually, you are writing both these terms the in terms of u dot and v dot, not just the u's and v's. And hence, because it's an implicit function, you have to do all that in order to define it. Okay, and what about the Jacobian for this? So here comes the shifted Jacobian. Just a quick, let me just fix this real quick. If I want to write it in terms of f equal to g, yeah, so let me just tidy this up a bit. I mean, all of the discussion is still valid. I just want to clearly write it. So this will be del u del t minus the Laplacian of u. This will be del v del t minus Laplacian of v, and this will be minus uv square, that is this, plus phi 1 minus u, and this will be uv square minus phi plus kappa times v. Yeah, okay. So now we have to form the implicit Jacobian. Now the implicit Jacobian will actually be written in this form. It's going to be df dy dot plus df dy, and it's not at all difficult. So these are all the submatrix of differentiation. Now remember, whenever you want to loop over the two variables, you need to do a final loop like this. Okay, so each row uh, value, so once you want to loop over a certain variable, you must say rho dot c equal to either 0 or 1, because you want to loop over u and v separately. Okay, but internally it always sets the variable correctly and there is no issue in that. Then you do the same thing, set stencil, then assembly begin, assembly close. If j is not equal to the preconditioner, you assemble j anyway, but we have already done it. So the functions are not that difficult, and we have set an implicit explicit problem. So once everything is set, I guess all that is left is to run the program. So let me just make the noise level a bit low, 0. Maybe 0.02. We'll increase the time later, but let me make Turing. So I've called the program as Turing.c, and I've also gone ahead and modified the make file. Then we do dot slash Turing. So DA refine is because we have defined a 3x3 grid. It's quite small, so you refine it 5 orders of magnitude. TS monitor solution draw. So whatever the solution we're gonna get, we're gonna draw the solution as well. So let's run this and let's see what happens. Okay, there you have it. We have weird looking oscillations. Okay, maybe I need to increase the number of time steps to maybe say 2000. And what is the time step? No, the time step is fine. So the initial condition was those 4 lobes, nothing else. I forgot to make it. You have these oscillating solutions. It's not gonna really die down. I guess we can stop. Let me just change some of the parameters. So let me change phi to 0. 0.05, and let me change kappa to 0.063. The diffusion coefficients can remain the same. Let me change the max time to something much larger, maybe say 15,000. And let me change the noise pattern to 0.15. So let's see, let's make the file. Let me refine it. Maybe let me refine it a bit more. Let's see if we can get something fantastic out of this. We've chosen phi to be 0.05 and kappa to be 0.063, something in this region. So we expect a kappa kind of pattern, that is this labyrinth pattern. It's almost like one of those labyrinth mazes that you might have seen in the movie Shining, where Jack Nicholson is finally stuck in a labyrinth like this. In fact, such patterns are also formed in ferrofluids when you subject them to a uniform magnetic field. This is the kind of labyrinth instability they form as well. Let's see whether it evolves to that. So it does seem to evolve towards something. I think we need to let it run for a while. So it's like the lobes are expanding outwards, and at some point it should start folding onto itself. After which the pattern will start forming that kind of a labyrinth nature. Well, while this program runs, I'll take this opportunity to end this class over here. The video will contain the rest of the evolution. It will be